Yeah, and we need to connect that audio jack also.
Can I? Yeah, here it is. No, we are using aux cable or should be zero. And you can unmute it. Of course, that's how we use it. Then it is fine. We don't need. No, it can bubble. Okay. Professor will give you the
Bhavani, do you need PPT or PDF? PPT, because there is some
others swap discuss.
swap display. So Zoom either put that.
Okay, run for
No, virtual I can display, they should not see that screen. So if we swap displays, see if we swap display and everything, these guys will see the screen, but the participants virtually will see the screen. So is there a way to
Can I use this one?
Yeah. It should be a way to move it. So that you see both. And also, so what do you see on the for the virtual?
You see the whole screen?
That's
Okay.
Okay. In the WhatsApp. It's also,
You can take control from here.
okay. Thank you.
Point.
This one is the point.
Okay. Okay.
Like we want to test for the virtual speaker also for the first 5 minutes.
Okay.
So after that we can go on. Like,
Maybe okay.
Sir has to unmute himself. Sir, did you unmute us?
it's like if you talk once again, we'll confirm.
Yeah,
that
yeah,
it's
this is-
working, then we can check it for the virtual speaker.
So should I talk now?
Yeah.
Yes.
Go and
We'll just both needs to talk.
Hello.
Is it no sir? Is it done? Yeah.
Hello.
No, it's
Vijay, can you hear me?
Yes, I can hear you.
He's speaking. Vijay, can you talk again? They're just checking the audio.
Yes, I can hear you.
yes.
can you also ask him to share his screen?
Vijay, do you want to do a dry run? Just show your screen. Share.
I have all the slides, right? So you drive the slides in your laptop.
Is he going to use the slides?
There's no need to change that.
As you wish. Vijay, so then I keep control of the slides then.
Yeah, I mean, I can't share the screen anyway. It says, okay, it will stop other screen sharing. I mean, should I even try screen sharing or just leave it like this?
Okay, try screens. Okay.
No, I mean, you can, it's better you can.
Okay, they're suggesting that me control that, so I control it. Okay. You just tell me when to move forward.
Okay.
But Sandeep, he's going to do one stretch, so it's easier, I guess, for him to
Then share.
share. Vijay, share.
Okay, but we are going to switch between different segments, right?
Yes. So I stopped sharing now. You can use share.
Okay, let me see.
Is he going to switch on his webcam?
And switch on your webcam also.
Okay.
Okay, I think. Okay, webcam on.
Yes,
Is that working?
give him some.
And can you see my screen?
Yeah, Vijay, make it full screen. I think. Yeah.
Okay, is this good?
Yeah. Okay, let's start. Hello. Good morning, everyone. My name is Shankar and I'm the session chair for this session on distributed integrated sensing and communication. This tutorial will be delivered by two speakers, Kumar Vijay Mishra and Bhavani Shankar. So I'll just give a brief bio of both the speakers. Kumar Vijay Mishra obtained his PhD and MS from the University of Iowa and MS in electrical engineering from Colorado State University. And he's currently a senior fellow at the United States Army Research Lab at Delphi. And he's also a technical advisor to Singapore-based startup Hertzwell and also Aura Intelligent Systems, and an honorary research fellow at SNP. And he has a number of awards in his name. He's the vice chair and chair designate of the International Union of Radio Science Commission. He's the guest editor of an upcoming journal on selected topics in signal processing. He is also lead co-editor for several books on radar. And the other speaker today is Dr. Bhavani Shankar, who received his master's and PhD from IISc Bangalore. He was also a postdoc at the signal processing lab at KTH Sweden. He is currently at the University of Luxembourg, and he also has brief stints in the industry, both at BSIM and SASKIM, and he was also briefly associated with EHUA. He is currently on the executive committee of the IEEE Benelux Joint Center on Communications, member of USF Special Area Team on Theoretical and Methodological Trends in Signal Processing. He was a co-recipient of the 2014 Distinguished Contributions to Satellite Communications Awards. Both speakers have research interests in radar systems, signal processing, remote sensing, and satellite communications. So I'd like to welcome both speakers. One of them will be joining online and the other in person. So just quickly to the audience, the Virtual participants may please put their questions at any time in the chat box of Zoom, and we'll be monitoring the same. The in-person participants can please ask their questions directly, and then maybe repeat the questions for the benefit of the virtual audience. So over to you, Bhavani and.
Thank you, Shashank. Thank you very much. It's nice to be back to my alma mater, but I've never been to this part of the building yet. So this is the first time. So at the outset, thanks organizers for providing us the opportunity to deliver this tutorial here at SPCOM. So we have sort of tried to sort of considering a wider background of the audience. So we try to make it in two parts. One is about on the fundamentals of ISAC. ISAC is a new term. We called it JRC, people call it JSC. So there's many things, many names to it. And then it would be a bit on fundamentals of the integrated sensing and communications, taking you through the journey on what was the motivation, how MIMO communications and radar sort of look like in this context, and then some considerations and architectures of ISAC. And then finally, we close the first part with widely distributed. I think that's the aspect that we want to look for, widely distributed systems. And then it's a very much an ongoing topic of research. So we really don't have anything sort of more fundamental and a large body of work. So we have a number of, we have a collection of works that deal with different aspects of distributed sensing and communication. So we're going to look at all of them, or some of them, to give you snippets of what is happening and then conclude it. So this we have been through. So acknowledgements, colleagues at the University of Luxembourg and Professor Nuria Gonzalez from North Carolina State University who helped us with the presentation material. And of course, the generous funding from the European Research Council, grant for Professor Glenn Utterston, and the Luxembourg National Fund just helped us with this. Okay, so start with some motivation for ISAC. Try to give it with two synergistic aspects, one more from the spectrum needs and one from the spectrum allocation. So, so for the spectrum need, I'll sort of use the automotive, which has been the very classical example in this case. So, I mean, cars nowadays are very much more intelligent than what they were before. So usually it's a lot of sensors in the car. So you would have a very low RF signaling to sort of test your tire pressure, you have ultrasound for your parking, your cameras, and then you have many other in-car monitoring sensors. So you have a number of sensors in the car, and different companies use different sensors. Tesla doesn't use LiDAR, for example, but some others use that. So there are a lot of sensors, right, ranging from the sound, the ultrasound, all the way to LiDAR. So, and then if you look at, as I said, many sensors, but we're looking at a couple of them. The prominent ones are radar, LiDAR, and camera. So all of them have their pros and cons. What we're going to focus here is more on radar. The radar is sort of an active device. It has to emit something to get back information from the environment. And then it has a quite good range, about 200, depending on how you configure it. You could also use it for short range. For example, if you want to detect a pole on the curb, so you want to avoid that, you could do it. It's a very short range, or even you could do long range like you do in the automotive cruise control. Accuracy is quite decent depending on how much resources we put in. But good thing here is that it's sort of robust to harsh conditions. So it doesn't matter whether it's day or night, lighting conditions, nothing. And then one important thing that distinguishes it from the other two are that you can measure Doppler. You can measure the speed of the. And then nowadays you get radar for a few $100. Whenever we write any proposal on radar, the immediate question that comes back is military things. And then the military technology is far more advanced in terms of hardware, and it's quite expensive, but we're looking more from a commercial aspect, which you get it for a few $100. And then, but The downside is that it does not have semantic information. All that you would see is some sort of points in the scene, but you don't have anything like a camera. You could distinguish between this and that. But that's also good in terms of, at least in the European context, it's very good because it's sort of privacy preserving. So you could put it anywhere you want. So LiDAR is good, very highly accurate, but it's quite expensive and expensive. You don't get Doppler, and camera has its own problems, the privacy problems, and then poor visibility, but it's a passive device. So you're going to look at radar. So the thing with the radar functionality, so usually people associate with Heinrich Hertz. So he was the one who sort of proved experimentally proved the existence of electromagnetic waves, but there have been several fundamental contributions, the series of developments that led to the radar, one of which was the millimeter wave generation. It was done by Jagdish Chandra Bose long ago, centuries before the onset of 5G, looking at millimeter wave. And then, of course, the radio wave transmissions. And the first prototype I would call was from Christian Holzmeier, which was called telemobilius program. And this was the initial images. And what does a radar measure? We'll come back to this a bit later, but very quickly, it sort of looks at different domains, gives you parameters in different domains. It looks at the radial range, how far you, in terms of if you measure the delay and you get this information. Velocity, you get it typically from the Doppler. And then you also get to know the reflectivity, how strong is the target, or how strong is the reflections, to sort of distinguish between targets, whether it's a metal piece or a human body. So you need to know that. And of course, the angle, which is the classical direction of arrival. And as these are impacts in different domains. Range is in time, velocity is also sort of in time, but if you look at it in frequency, angle is in space. So, but we would focus here on range and angle in the rest of the topic. So what guides the radar performance, just to have a quick understanding? Here's a simple example. You have a car and then you have two other cars approaching, and then assume that you could put a wide beam. You just have a single antenna, because you have a wide beam here. And then I want to distinguish between these two cars. From the perspective of this car, there is a minute difference between the path that's traversed by the radar wave or electromagnetic wave to these two cars. So this is this minute path difference, and this path difference manifests into delay, and then you have to measure this delay. So you have to measure minute changes in delay, and that is possible if you have very high bandwidth. So if you have a low bandwidth, you would get a big blob like this, but if you have high bandwidth, you could actually distinguish between the two. So you are able to resolve the two targets with high bandwidth. Many times, just high bandwidth, it's sufficient. Here is sorry, the picture is not rendering well, but you could see here, typical thing is a classical use case here is that you have a big truck and the kid coming out of from the truck, and then your car is supposed to stop. Because it sort of, if it was just a truck, it's a parked truck, you could move on, but then there's kid coming out. The problem here is that the truck has a very large reflection, and the kid coming out has a very a feeble reflection. So you need to have the possibility to distinguish between both the targets. And then here you would need both the range, which is the small differences in path, and also an angle difference. And then whenever we look at angular resolution, the ability to separate in space, not in range, which is in time, but in space, is, you need multiple antennas, and that is where we go into the concept of MIMO radar. So you're going to have a lot of sensors on the cars. At least the radar sensors are used for particular applications that we said, able to provide sort of support to the driver. And then the cars are all software managed now. Many of the cars that we drive sort of don't shift gears because there's a glitch in the software. It's an automatic vehicle. And then they're not connected. Different cars have sort of different connectivity. So some are sort of within the body, within the in-cabin, and then you have connectivity to the outside world, to different aspects. You got the B2B, B2X, and a bit more sort of, if you're a bit more optimistic, some to the satellites and so on. But once you have the ability to software manage, collect data, and process it, you also to connect. So, so these connected vehicles, for example, sort of can help us, in many things. One being the sort of security and safety of the driver and the other vehicles that are sort of in the road situation. And then it's also sort of helps you with more the driving comfort. For example, becoming more like your car is now a mobile phone. So you sort of get into some place and then it probably downloads all the things that you want to download. So forth. So it's connected. So it's more the comfort level. You have the security. So you want to sort of pass on information about warning signs, and you want to enforce speed limits. Sort of also in platooning, so you would have all this information, and a bit more on the societal in a sense of trying to reduce the emissions and trying to avoid routes that are congested. So connected vehicles are sort of the norm nowadays. And then when we go into the connected vehicles, your sensors, you have the connection, is to understand what is needed for this connection, and how much data is needed for this connection. It again depends on what do we want to share. Simple things, a few megabits per second. And then if I want to really go on to the sort of autonomous vehicle that you're looking at, and that there are different categories of autonomy. Level 3, 4, I guess, is the presence of the driver when needed, but the car is supposed to drive on its own. So you would require such a high amount of data. For instance, if you want to look at it from the automotive perspective. And of course, if you want to put some numbers to it, it's also quite, even though the price for supporting data is going down, but then the amount of data that you want to run, this is per car, but then if you have many cars on the road, you need so much more. There have been some works, there have been some technologies which are sort of able to support this. One is the SRC and then the CV2X and the LTE, but these are not sufficient to support such high amounts of data. This was probably for some quick messaging and a simple exchange of data, but if you want to look at such high data, the existing standards or the existing allocation of bandwidth for the standards are not sufficient. So in that sense, if we look at one canvas, the aspect of the canvas, we have the autonomous vehicles, they need high bandwidth for two reasons. One, you need to sense, and sensing in terms of accuracy, in terms of range accuracy, you need very high bandwidth. And then the other thing is, okay, I have the bandwidth, I do everything, I collected information, but the cars are connected, so you want to pass on this information, and then you need bandwidth for that. So that is the bandwidth. And here's a quick thing where the sensing is nowadays moved to 77 to 81 gigahertz, a 4 gigahertz bandwidth sensing. And this is what is used in automotive in-cabin and exterior sensing. And then so you have 4 gigahertz of bandwidth here. What IEEE supported with these aspects were about 30 megahertz of bandwidth, which is sort of nowhere near 3 gigahertz bandwidth you look at. So one possibility is to sort of use this bandwidth for this sensing and communication. The other thing is, of course, going to the low terahertz, but you're still in the millimeter wave, higher end of the millimeter wave band, where you can use that for short range automotive sensing, but also use it for communication. So that's one aspect. So you're going to look at it. We have an issue from the sensing requirements per se, and then the automotive things with the level of autonomy. We're looking at the connection being, connectivity being the needed aspect. So you need bandwidth for both. And then you have the other aspect is, okay, this is what we need, and what is happening here is that in most of us, we know that the wireless communications is sort of taking over all the frequencies from keep mentioning is everywhere I go, from DC to daylight. So everything is being sort of considered for the wireless communications. So you have a number of, now if you look at 5G, there's sort of look at the increased number of devices, and one use case for 5G is also the connected case, I guess, the automotive scenario. So I mean, this is very classic, I think, so I will not go into it. So here, the idea here is that the proliferation of the mobile communications is much more than the automotive. And then there's been a sort of cohesive approach from the automotive community, so from the wireless community, in a sense that, there's a protocol that is sort of now, and you could use that protocol everywhere. But, in an automotive scenario, if you want to use a radar, I use a radar on car 1. It's not not, I would say, coordinated with the radar on the car 2. So everybody does their own allocation. Everybody is using their own power. And so what would happen is some sort of interference scenario that's going to come up. And there is no cohesiveness in the development of the radar. And so and then of course the volumes are much lower than the cellular communication. So there's been more bandwidth that is being allocated to cellular communication. Of course, there's much more need here as well. So in that sense, there's an increased spectrum allocation for wireless communications. And then if you look at it, look at the allocations, so you would see that for every band of consideration where there is some sort of radar operation, there is an adjacent sort of allocation to communication. So here now we sort of had the automotive radars which were at 24 gigahertz, but then now moved it to 77 to 81, because 24 was allocated somewhere else. And then now in the high, this is the millimeter wave band, if you want to call it. So you have the 8.2.1180, and then we got about 1 millimeter wave filings as well. It's not just automotive radar, it's sort of automotive radar that's sort of being affected. Even I was been working on satellite communications earlier. Even though satellite communications come under the realm of wireless communications, the allocation is predominantly for wireless terrestrial communications and near-Earth communications that you have UAVs and HAPS. So here's another non-millimeter wave spectral allocation. So it doesn't, not necessarily in the millimeter wave, they've been sort of taking over of the spectrum across the board. And then here was one example where what was used for ship and airborne radars from the Department of Defense in the SNC band is now moved to wireless communications. And then 24 gigahertz, this was what we at University of Luxembourg, we were involved in a project where we were using 24 gigahertz radar sensors to monitor the breathing activity. So that gives you non-contact abilities. So the breathing sort of gives you movement of the chest wall, and it's a periodic movement. So you use your Fourier series and then try to get the frequency. That was done by using radar, but we are now forced to move to 77 to 81 gigahertz. So there is the spectrum need, then there's the allocation. Both of them do not sort of go for a dedicated hour of spectrum to radar. The point with radar is that it needs to be always on. You need to sort of survey, there's a surveillance going on all the time, and it's not switch on, switch off. So you need all the time, and you use all the power you need, because unlike the communications where you have the path loss, which is R square, radar is R power 4. So you would always want to put full power all the time. So you don't have this concept of cognitive, I have something like what we have in the communications. I could interlace something else with the communication spectrum. That doesn't happen with radar. And radar wants to use all the bandwidth, because higher the bandwidth, better the resolution. And this leads to sort of concepts of integrated satellite images, like integrated sensing and communication. And this also sort of been considered in 6G, where you have the joint communications with radar. And then there's also this integrated sensing and communications emerging technology. It started in ComSol, but I guess it's now pretty much everywhere.
I have a question. Is that the spectrum we talk of the data, I guess those are mostly unlicensed.
77 to 81, I think is licensed. It's licensed. He was asking if the radar bands that I mentioned were the licensed or unlicensed. So it is 77 to 81 is licensed. 24 was licensed because we have an industrial product coming out, and now I think it's being given. So there's probably reallocation of that.
If you use unlicensed spectrum for radar, I think that particularly for V2X application, you would need high reliability. So I was wondering how can you ensure high reliability in unlicensed spectrum?
Agreed. So that's what I agree. So that's why we sort of have to use dedicated bands for radar. Unlike, for example, wireless communication, we have a protocol support to do some things. Radar doesn't have it. Okay. The other thing that sort of if you look at it now, we're going to now focus on the millimeter wave band for the thing, which sort of is now touted as the panacea for sensing and communication. Of course, for the communication, the throughput or the capacity, the ability grows linearly with the number of orthogonal resources and the bandwidth. So the orthogonality resources, to some extent, you could say with the number of antennas. So there comes the MIMO, and then you have the bandwidth. So if you go to millimeter wave, you have higher bandwidth. So I wouldn't say orthogonality, I would say reuse with little interference. And then for the radar, you would need bandwidth because it improves the range resolution. And then we also see that higher the number of antennas, you would have better angular resolution. This is the classical signal processing. So you need wide bandwidth. And then the other thing that has been happening now is the miniaturization of components. So this would be a radar chip. If you look at any TI, AWR or IWR chips that are coming out, it's quite small. Unlike what we see the classical radars on in the airport or something, wherever the concept of radar, it's a big dish rotating, so that's sort of not there anymore. It's like a mobile phone radar. And so the idea here is from a so there's more to spectrums, sharing, and everybody wants wide bandwidth as limited bandwidth, so let's put the two together. But then also from an industrial perspective, sort of doing it, and then for example the data and the communication, more or less apart from the processing, from the RF, on the RF front, then both of them do the same thing. Generate electromagnetic wave, transmit, receive, and then convert to baseband, after which you do a different sort of processing for communication and different processing for data. So the RF development could be sort of synergized between the radar and the communication. And then, in fact, the idea with the radar companies is that they would like to piggyback on what the communication companies are doing because it's much more volumes there. So they sort of try to reuse the hardware that one would develop in millimeter wave band communication. So this is more the industrial motivation for sort of RF hardware reuse and development, minimizing the development. So the millimeter wave band is quite extensive from 30 gigahertz to 300 gigahertz, but not everything is useful. Only because you would have a lot of atmospheric propagation aspects that sort of hinder the that sort of attenuate the signal. So you would have atmospheric absorptions at certain aspect, at certain frequencies which you would like to avoid. When you do all those things, what you have is about 40% of the band available. So it also depends on the technology. Do we have the technology to support a particular frequency? Right now, you have 77 to 81 gigahertz. We have chipsets coming in. There are some things for 120 gigahertz, but beyond that, it's more in-lab demonstrations. So we don't have technology. In my understanding, but maybe I'm wrong. And then, as I said, the millimeter wave was sort of Jagdish Chandra Bose was the one that started the millimeter wave thing, and then the millimeter wave was initially used in automotive radar, but then only recently sort of started to be used in at least being considered for 5G. We just try to just give the few notions on this, and then we move on to another aspect. So this is quite common for both radar and communication with the millimeter wave. You would have poor received power because of the path loss, and then of course you have wide bandwidth. Your receiver front end is sort of operating on a wider bandwidth, so you're going to collect more noise, KTB. So, but the thing is that you would probably need to use MIMO, massive MIMO, and so on. And then the fact is that you can compact the antenna, so you would have a very small form factor, and that's what was mentioned here. And then of course you would have high sampling rates. So you need to sort of come up with a sparse channel, a clustered model in time and to sort of handle high sampling rates. And then there are some implications is that you would sort of go for, when you have large arrays, this classical thing to going for mixed analog digital components, hybrid analog digital reforming, 1-bit ADCs, BACs. Wideband processing, this is something that is coming up. Now, for example, if you have very high bandwidths, the classical notion of bandwidth where the time delay is made into a phase shift no longer holds. It becomes a time dependent, so the frequency dependent phase shift. So you need to look into wideband processing aspects, but more important is the shorter coherence time. So you need to act fast for your block fading or anything that you want to assume. So there is no free lunch here. So millimeter wave millimeter wave is what we're going to look at, but it comes with certain aspects that we should be we should be aware of, and it would have some implications that we would see later in the tutorial. Very quickly, MIMO communication, just to put the MIMO the way MIMO has evolved and the way radar has evolved. But I started my PhD, there was a time when we had these two papers from Teletar and Fushimi from the U+ coming up. That was the one that started the MIMO. And then now MIMO is ubiquitous, part of everything, and we have support.
Quick question from the virtual audience.
Yeah.
So, Vijaya asks, can the bandwidth be aggregated from different bands to improve resolution? And what kind of radar waveforms, CW pulse, etc., are suitable for what spectrum band?
I mean, there are some things we call it spectrum stitching. So you have spectrum. Yes, if you want to focus only on range, you could stitch the spectrum. You would have, like what you do carrier aggregation in communication, you could sort of stitch the spectrum. But it becomes more complicated to handle Doppler in such cases. You have different bands and different things. And with regards to the waveforms are not are agnostic to bands. It's more the functionality. So, for example, if it's a continuous wave, you never know what was the range. So you need pulse signals. And then if you want to do the pulse, then you would like to have, I'll come to that later. There is something called the notion of ambiguity function in a radar, how good you're able to localize in time and frequency. So the waveforms should have an ideal ambiguity function. So we're going to look at that. Those are the characteristics. It's not really dependent on and the pulse waveforms, all of them typically have the same performance characteristics. You give more bandwidth, it has better performance. Okay, so everything started off with point-to-point MIMO. We started off with we had two notions. One was the multiplexing gain, and then you had the diversity gain, and then came the diversity. Yes.
So the radar chipsets that you showed before, are they inherently on full displays or can you do with half displays?
No, they. I don't know. Yeah, they're all half. I mean, they're different transmit receive antennas, and they are shielded to some extent because radar is emitting. Because it's half duplex, you have this pulse transmission. So you used to be that you transmit, till the time you transmit, you keep quiet. And then you start receiving. But then till the time you transmit, you're blind. You don't know what, you don't get any target in that time. So if you could simultaneously transmit and receive, then you're able to get the blind range is what we call, that becomes 0. But then the point is that you need additional antennas. So that's one sticky point. Now you need additional antennas. That somehow is being used in radar. MIMO, then it became multi-user MIMO, and then sort of now this is a common thing in many of the communication standards. From a theoretical aspect, the interesting things, I think some of the people in the audience have worked on it. The capacity analysis of multi-user MIMO on the MAC and the broadcast. And then people started to look at precoders and beamformers, and then that led to sort of a series of works on using optimization techniques for doing certain aspects like it. And this is exactly what we do in radar. So we have some things, and then sort of go into more optimization aspects, trying to solve some problems. And then we moved on in communication, then moved on from point-to-point multi-user, but when there was a single base station, one entity controlling many things in itself, to this sort of coordinated multi-point. Coordinated multi-point in the sense that there's coordination because there is a protocol, or there is some sort of understanding or a synchronization or coherence between multiple transmitters serving multiple users. So this is usually a protocol support. And then you would have, for example, things here where you could sort of coherently transmit, and then you could have a fast selection between the different base stations. And then also on the uplink, similar things. Like today, look at the evolution from point-to-point multi-user, and then non-collocated MIMO. And then a bit more till here, you have everything supported by the standards. And then you could think of a bit more research-oriented, non-collocated multi-cell systems, where you could have flavors like centralized, where you collect all the information needed and then you put everything in a central node. The key thing here is that you have all the information at one particular set, and then you have everything which is done in synchrony, and then you have sort of coordinated, where instead of doing the whole cell, you do it in sort of simpler clusters, and then you have the cognitive. And then recent work also sort of looked at more distributed system, where you had a collection of transmitters and receivers, and then each of them had their own sort of had their own RF RF oscillators. So this means that there is no synchronization between all of them. There is no protocol support to sort of synchronize them, or maybe there's not a protocol support to synchronize them on the bit level. For example, if you're looking at gigabits per second, so you would need sort of nanosecond synchronization between the different nodes, which probably is not. You would probably have 1 millisecond synchronization. It's a coarse synchronization, but you nonetheless, this is what is moved on from point to point all the way to distributed systems, where you would have these kind of sort of the key here is that there's no synchronization; they're all independent systems. And this was one of the methods that was initially touted for NASA. And then, of course, the latest thing that is happening here is in terms of the signal processing critical layer is massive MIMO. Okay, now we're going to radar. So that was the evolution of communication. Now, if you look at radar, then this is what it would do. So you would transmit an electromagnetic wave. An electromagnetic wave is sort of characterized by its amplitude, frequency, and polarization. You transmit, it's impinged as a target, it's reflected back, and then you would see some changes in all of them, or some of them, depending on what aspect that you want to measure. So, if I want to transmit, usually, as I said, you could actually transmit a sinusoid. If you just transmit a sinusoid, it comes back, but then you will never know what was the delay. because you're receiving a sinusoid. What you could actually measure is if the target is moving, you hit the target, it comes back, you could measure the change in frequency, that is Doppler, but you never measure the time because you never knew when there is no start and end. So that's why people started to look at pulse Doppler, pulse system, where you have a sort of pulse, transmit, and then you know exactly that this is the pulse that I transmitted, and then for a certain period of time, sort of unambiguously associate the reflections to a particular pulse. And then, so the reflection, if I transmit a pulse train like this, I would get a reflection like this, but you would have the angle, the delay coming in here, which sort of gives you the range, then the Doppler, and then you change the battery. I think you should change the battery. Yeah, then you have the reflectivity, which is the alpha, which is sort of the channel coefficients, if you want to call. So again, there are things that we would like to do. High range resolution, I've been continuously mentioning that we would need very high bandwidth. High angular resolution is not mentioned here, needs antennas, and then Doppler resolution needs a lot of time. So you need to sample. Sort of, you need to dwell on the target for a lot of time to sort of get good Doppler resolution. Okay, so this would be the classical radar thing. So you would pulse shape. You would do the match filter, very much like the communication, where you would have a square root cosine, raised cosine filter at the transmitter. You would have a square root raised cosine filter at the receiver, and you want to make them Nyquist. Here it's more to improve the SNR. So if you use the Cauchy-Schwarz, you would say that this would the match filter is the one that's best for sort of improving the SNR, because as I said, it's not mentioned here. The radar sort of is called the non-coherent reflection. So you would have the power that is received is varying as R⁴. In communication, it's R². So you need to build the SNR. Normally at the radar receiver front end, the SNR, if you measure before the pulse shape match filter is negative. And then you would do some processing to get which I will sort of mention a bit more about the processing when he looks at the waveform. So that was a single transmit, and see, this is what you would do if you want to transmit from one antenna. But then if you have MIMO radar, it's a bit slightly different from the MIMO communication, but MIMO gives you spatial extent that you want to use to improve the angular resolution. So we know that if I want to have a very narrow beam, I need to have a very large aperture. So it's in a sense of now the kind of things that we are looking at, the electronically shaped beams, I need to have a lot of antennas to have a very narrow beam. So instead of, for example, what MIMO radar does is to minimize the number of transmit and receive antennas, RF elements, so that you have a particular, for a given beam width. So the idea here is like this. So you would have, for example, I'm having here 5 transmit antennas, which are in orange. It's very feeble, I think. Okay, I can go here. You have the 5 transmit antennas, which are in orange, and then you have, if you look at the classical spatial sampling, you would like to do it λ/2. But here you're not doing λ/2. You are separating them by R times λ/2. R is the number of receivers. Okay, and then I have 3 receivers here. The receivers are put at λ/2. So now, if you look at this, this is a subsampled sort of antenna placement for the transmitters, and then you have a Nyquist sampled antenna placement for the receiver. And then when you do intelligent, when you transmit intelligently and do some intelligent processing, what you would get is and you're having here of 8 elements, and then what you would get is about 15 elements. You get an antenna array of 15 elements. So you could reconstruct an antenna array of 15 elements. So this means that with 8 elements, I am getting a main lobe or a beam width which is commensurate with 15 elements. So you're sort of reducing the amount of antennas required for that. So this is what we look at in a MIMO radar. So this is where we sort of depart from the MIMO communications in a sense of how we achieve the sort of requirement. And then 2 things here, we'll come back to this again. There's the co-located MIMO. Co-located MIMO is where all the antennas see the target. All the targets is sort of appears similar to all the antennas. So it's more like a far field assumption. But all of them see it at the same time, or sort of look at it from the same perspective. When you have widely distributed, we also come back to that, you would see different aspects of the target. We'll come back to that. Yes. I don't know why it's. Let's see if it works. Okay, it's working.
Yeah, the previously, archives.
And you're using it.
I'm sorry, sir, I was just.
No problem. Yes.
Is it mandatory that to do that? Because the virtual array creation is, I understand, you want to create a longer receive array by doing intelligent transfer. But you can still go with another spacing in the transmitter itself, like in case you want to go for classic beamforming from the transmitter point of view.
It's interchangeable. You want to put lambda by 2 at the transmitter, but then a subsample array at the receiver is fine. So idea here is that you're going to convert. If you look at this as a frequency, as an impulse response, so the receive array is more like a convolution of the thing. So you're filling the spaces.
I understand, but if I'm not interested in creating the virtual array, I just want to use this regular lambda spacing in the transmitter, regular lambda spacing in the receiver. That is still
Yes,
viable solution.
that's still a viable solution, but then your beam width is limited by the number of transmitters.
Correct. But only thing is that the grating lobes problem will not.
Here you have grating lobes because you're subsampling the array. When I transmit, I would have a lot of side lobes because you're subsampled. But then these are removed at the receiver. So you have, but then you remove them at the receiver.
In the classic radar illumination point of view, we want to focus if we are like steering or sweeping the area. So you need to take care of that because of the thing.
No, I mean the whole idea is that this is what I'm more interested in. What is there? What is happening at the input of my detector? So if my receive beamforming is removing the grating lobe by the time I get, this is usually done before the detector, then I'm fine. So that is I have the thing here is exactly what you're mentioning. Then you have the classical phased array radar where you put beams. You put beams, and then you have the same waveform being transmitted on all the antennas, but with some phase shifts. And then you put, and then the phase shift is such that you want to focus a beam at a particular point. So since there's only one transmit antenna, one transmit waveform that you're doing, so you're going to put one beam. And then it forms a coherent beam in a very specific direction. So it has the higher, it has a very good gain. It has a very good gain. And now if you sort of localize the target and you want to track the target, you need such a beam would be very helpful. It sort of puts the beam, it tracks it. But then, as I mentioned here, if I want to have 15, beam, if I have P transmit, R receive, And if I want to have a sort of an array of length TR lambda by 2, or the beam width which is commensurate with TR elements, I need to have TR elements for the phased array. But on the other hand, MIMO radar, when I say you sort of MIMO radar actually is isotropic transmissions. You transmit orthogonal wave. You just transmit some waveform, for example, you know, CDMA code, for example, different CDMA codes on the different antennas. So you're not beamforming anything on the antennas. So you're just transmitting, so it's illuminating the whole environment. So in that sense, you don't have the ability to track. So you're illuminating everybody. So, and then there is no SNR. Sort of SNR is also very poor because you're not focusing it. It's more a mathematical construct that when you receive, you're able to distinguish between different targets, because that you would couple your transmitter with the receiver. This is also that, and then what you transmit is also important. That's it. So the MIMO radar, in a sense, is typically isotropic transmissions. It's transmit everywhere, and so it's good for searching. If you don't know where the target is, you eliminate everywhere, and then the receiver will sort of find out where it is. And then it doesn't have any meaning because you're transmitting incoherently from all the transmitters. But it's good in a sense that you could create a virtual array which is much longer than the number of elements. So here's a bit more on the orthogonal. So here what we have is the MIMO radar. So you would transmit from for example, here I think of T transmit antennas. So you're going to transmit different waveforms from these antennas. No beamforming, isotropic. And then we sort of say it's orthogonal in a sense that, as I mentioned earlier, so you transmit, you receive, and then you do a pulse beam for a match filtering. So the match filtering, you sort of, at every receive antenna, you match filter to all of them. So for example, I transmit with 3 transmit antennas, I transmit 3 waveforms. At each receiver, I would have a match filter, each match to the 3 of the waveforms. So now if I have 4 receivers, I would have 12 match filters. So you have 12 outputs coming out of 4 receivers, and then sort of then you could. So this is what sort of now this 12, if they're distinct, if you could distinguish between the 12, if all the 12 are separate, so you're essentially having 12 looks at the same environment. So you would have this, or you would have 12, would sort of improve the resolution because you have 12 looks at the same, so you could distinguish between the different sort of closely spaced targets. So this is what the key here is, to get these 12 to be separate. So you're able to distinguish between these 12 outputs to get them differently. That you could do if you sort of have some idea here with the orthogonal filters, where you would have the match filters where the output, for example, phi 1, the match filter match to P naught will not have any output from the waveform P1. So if that would be the case, then you would have all the 12 to be sort of separate, and you would get your virtual array. And then the ambiguity function I was mentioning, this is what characterizes the data waveform. So ideally, this is nothing but I would call sort of if you look at time frequency analysis, this is what it looks like. So you would have the time and the frequency here. So this is a 2-dimensional plot, and then you would want the radar waveform to pick up only the target at that particular delay and at that particular Doppler, and eliminate everything else. So essentially, you want this to be an impulse. This thing needs to be an impulse. Okay, impulse at the delay and at the Doppler. But typically, that doesn't happen. You would have ambiguity functions like this, where the reason it's ambiguous is because now if you look at it, you don't know where this is a range, so you don't know where the target is. That's why it's called ambiguous.
You said the tracking is the
Yes, you don't transmit in the direction of the target.
Not really tracking the target. Another thing is when you do.
I mean, the idea here is that you know the target is in a location, so you would like to exploit that, and so you want to put a beam to that direction. In MIMO, you cannot be there, so to transmit it.
But now we are talking about use cases. But won't it create a lot of when you have a lot of cars around it, MIMO radar.
Yes, it does create a lot of interference, but the waveforms are. The other problem is that, unlike the wireless communication where you have a protocol that supports sort of allocations, there is nothing like that in radar. So you're not going to look at this in this tutorial, but then you could have, for example, the waveforms that you want to transmit, you could transmit different ports, different CDMA ports, for example. And then these ports tend to sort of be orthogonal to the randomly or choose them according to something. You could sort of mitigate the interference to some extent. And also in some particular waveforms, they're inherently sort of immune to some interference. So it's basically that is what we have to exploit. There's no coordinated effort. Of course, there's going to be interference. Okay, and then very quickly, for people who are looking at difference, the nested arrays, sparse arrays, and then co-arrays, and so on and so forth in the literature and direction of arrival estimation.
Yeah, another good question. Does typical radar channel need to have a large coherence time? Is it you need large dwell time to get good Doppler resolution?
Yes, I mean, again, the question is how large is large? Because, for example, we're going to transmit in 77 gigahertz. So your typical pulse rate is much less than a microsecond. So you accumulate hundreds of microseconds, still a millisecond. So it's still fine. So that's the. You transmit very fast.
Also, I think can we use the typical communication standard models here? It's kind of information that we're interested in.
This is what we have to be a bit careful. What we could use is some sort of path effects, maybe sounds. But then the classical thing is that the radar wants the radar knows what it transmitted at the receiver, and what is unknown is the channel. And in communication, you don't know what is transmitted, but you assume that you know the channel. So you need to find out what was transmitted. So in that sense, the channel modeling is a bit different in radar because the channel modeling here has to do with the targets. And then there's different depending on the way you transmit, more or less like communication. There are some channel models for target models we call, and these are called swirling models. So swirling 0 is more a constant, swirling 1 has a certain characteristic, swirling 2 is, and then swirling 3 probably again. One of the swirling is more like a Rician field. So you could ascribe some things to the target. Okay, so MIMO radar becomes a sum co-array. People who want to look at, I'm not going into this detail, but then classical things that we've been looking at in geo estimation is difference co-arrays, but here it becomes a sum co-array. So your delays that you get is of this form, and so if you could separate the delays into the large and aperture length, so you would actually get all that. And then finally, like communication, we also have in radar point to point, which is what we call monostatic. You have the transmitter and the receiver co-located. In some systems, the transmitter and the receiver antennas are the same. If it's pulsed, and then if it's more continuous wave transmission, you would have two separate. But then the key thing is that the transmitter and the receiver are co-located in full synchronized manner. The transmitter and the receiver knows what was transmitted, and then it would work. And then even if I put an array of transmitters, an array of receivers, the idea here is that the angle, the range of target, everything is identical for the transmitter and the receiver. This is the thing. And then this is very common. This is not multi-user, but then this is what we call the bistatic. Bistatic is where the transmitter and receiver are not co-located, they are separated. And then separated is when they're going to have independent oscillator, independent RF change. They're going to be some sort of lack of synchronization. And then the receiver is going to always look at the path that comes here. But sometimes you could also have a direct path. And this direct path could be a boon or a bane. If the direct path is very strong, it could saturate your receiver. Or if the direct path is not strong enough, if you're able to resolve the direct path, it could give you you could use it for synchronization. Okay. So this is the idea here. But then what you're going to measure is not this range. You're going to look at this bistatic range, which is this. And then also the Doppler. You're not going to measure the Doppler as seen by this thing, but because you would see a composite Doppler, because you have a transmission here that is affected by the Doppler. That's seen from this, and then there's a Doppler. So this is the bistatic mode. The key difference here is that the receiver can be passive. It need not be any transmitter at all. You could just put some receiver and it can start receiving. This has been a very classical thing where these was the TV transmitters, and then you have a lot of passive receivers. So used for localization. And then this leads to some sort of multi-cell system, which is called multistatic, where you have a number of transmit receive antennas, radars, and then each radar could act in a monostatic manner. It could transmit and receive its own signal and process its own signal, or it could receive signal from somebody else. But like in the COM for the coordinated multi-point, there is some sort of backbone here, because there are very few of these radars. So you could sort of collect more information and send it to a central node and then process. It's more, you do local processing to some extent, but then you also do centralized processing. So that information is more on this, the split is typically more towards centralized. And then you have information fusion, you get information from everybody and you want to fuse them. But then this leads to what we call the widely distributed data, where the split between the local and the central processing is tilted towards the local processing. You do much more at the local processing, and then you have really simple things that you want to put it to the central receiver and then you sort of fuse them. So that is why it leads to the widely distributed data. And I guess I would give, now I stop here and then I go to Vijay. Vijay?
So here, the direct part, it really depends on how far the gates and others are together. Because you transmit a pulse, if the reflection is going to arrive after the pulse is finished hitting the receiver, then it doesn't matter at all.
Whenever I get a pulse, I would always have, for the receiver, it will always blind as to when it sees the pulse, it puts it as another target.
But if you know where the transmitter and receiver are,
if you know that,
approximately know when the pulse will come, start, and
okay, if you know those things, yes. But then if the point here is that this is sort of direct path, so you would have an R square path loss. This one is more the radar non-coherent reflection. This would be R power 4 path loss. So if this is very strong in time domain, spread over. If you just okay, if you're transmitting one pulse, then yes. But normally you don't transmit a train of pulses. Vijay?
he shares it to take over.
Yeah, but I don't know what. It's quite late for him. Probably slept off.
Yeah, I'm here. Should I start? Should I share my screen?
Yes, Vijay, I have taken much longer than what I was supposed to. So you are going in gigabits per second now, I guess. Okay, you can share.
So I'll share my screens just so that I have a little bit more control over the slide, if that's okay. Can you hear me?
Can you increase the volume?
Yeah.
Yeah. That's it.
Yeah, can you hear me?
Can reduce it. Let's put reduce a little bit. So it's getting.
Can you hear me?
Yes, Vijay, we hear you.
Okay, so I'm sharing my screen. I hope it's visible there. So hi, good morning, everyone. I'm joining from Washington, D.C. It's almost 1 a.m. here. Yeah, very happy to join this tutorial. Bhavani presented a number of considerations on why we need joint radar communications, and separately, what are some of the typical communications and radar system considerations. And now I'll pick up right where he stopped. That is, when we join both radar and communications, what kind of topologies are there? What are design considerations? And then I'll continue with some of the waveforms, because waveform design is one of the important aspects of joint radar comms. So we'll review some of that material, and then in part 2, we are going to actually use some of these design parameters or waveforms, and we'll see what kind of applications are there for in particular for the distributed radar comms. So I think Bhavani alluded to some of these things before, but now we'll go into a little bit more detail here. So in joint radar communications, depending on whether we are sharing a particular hardware unit at the receiver or at the transmitter, or we are using a common waveform, or there is some kind of joint processing, there are a few broad categories of ISAC systems. So the very first one is the spectral coexistence, and this is one of the legacy systems. I would say for legacy systems, this is very beneficial because you do not have to change the hardware a lot in this case. So in spectral coexistence, radar and communications hardware, they operate separately and they access the channel independently. So obviously, if they're doing that independently, there is no synchronization between radar and communications. There will be interference from radar to comms and comms to radar. So in spectral coexistence, most of the processing is focused on these individual radar and communications receivers. And the processing, the goal of that processing is to mitigate the interference from one to other. So as I mentioned, that this is very good for old systems because we cannot change the hardware in old systems or something that has already been deployed. So a very good example of this system are the old foliage penetration radars, which operate at VHF and UHF bands. And there's a lot of interference from TV and broadcast stations at those for those radars. And typically their approach is that they would simply notch out the interference at those frequencies because these are very wide bandwidth systems. So if there is some interference in some part of the spectrum, although lead to deterioration of range resolution, it is still within the tolerable limits. There may be some information exchange sometimes. For example, at C-band, we have US Navy operates a maritime radar, C-band maritime radar, and some frequencies are also used by CBRS systems in communications. And typically, at least for certain applications, this communication system actually shares information with this maritime radar. For example, the radar may communicate to the communication system that you can lower your transmit power levels, because this is at this particular time we are going to use radar more often. So there may be some kind of information exchange. Otherwise, the changes in hardware are minimal, and most of the processing is at the receiver. So this was one of the old methods, but as with the advent of new radar and communications applications, this was not a very efficient way to share the spectrum, because in any case there is a lot of interference because they are operating independently. So the focus for the few years shifted to what we call as spectral co-design. So in spectral co-design, especially if we are building a new system, we start from scratch, and we actually try to find out if we could use a common waveform, which could be used for radar applications, but also carries communications messages. So we may try to devise a new waveform, and if it is altogether a new system, we might want to design a new transmit or receive unit. So for example, automotive radars, this is a relatively new application, and the new chips are being manufactured pretty every different companies. So they may try to incorporate this comms plus radar modalities within those chips. So this is a co-design, spectral co-design. And in this category, we also have opportunistic excess of spectrum. So for example, there may be a communications waveform that is already available, or communications transmission that is already going on. And there may be a case where a radar that is co-located may try to harness some information from that communications waveform. So we have some examples in part 2 that we'll see where this opportunistic spectrum works very well. And within the spectral co-design, there is a large body of literature on what we call as MRMC, where both radar and comms, they're not single antenna, but they are MIMO systems. And this is a more complex problem. But at the same time, it gives us additional degrees of freedom, because through antennas, we might even be able to differentiate radar comms in some applications. So joint MRMC also falls in spectral co-design. A third category, which is somewhere in between, is where the communication signal, let's say a downlink signal, it is reflected off target, and then the radar receiver receives this communication signal with some target information and actually decides to use it along with its own signal that was reflected off target. So this is what we call as spectral cooperation, and we'll see an example of that in part 2. All of these, so just on the terminology, all of these, we are still calling them broadly as dual function radar comms, or ISAC, integrated sensing and communications. I would say we just stick with either ISAC or JRC, but then there in the literature, you may find some difference between dual function radar comms as a great body of work. Most of the applications initially, they were at the lower frequencies, as Bhavani mentioned, but now we are moving towards high frequency like millimeter wave or low terahertz bands. And in those applications, as far as radar is concerned, there are a lot of vehicular applications. And communications, now we are seeing millimeter wave and terahertz communications. So I have to mention this here that as far as radar is concerned, there were other applications for radar at terahertz and millimeter wave long before automotive radar came into picture. So we have cloud radars we rate at millimeter wave, but they are vertical pointing radars. So they don't cause much interference to other radars because they're always looking in just one direction.
Hello? Professor, we are not able to hear you. The connection issue from his end. Sir, can you please rejoin?
Hello?
Yeah, we are able to hear you, sir.
Okay, I think I got disconnected. I don't know why.
Yes. Can you please reshare your screen?
So I was explaining that there were other applications as far as radar is concerned at millimeter wave and terahertz, but the spectrum sharing wasn't an issue because there were fewer communications applications, or these radar applications were very specialized in those parts of the frequency in the electromagnetic spectrum. But now with the entry of vehicular communications and radar, the interference is a concern at higher frequencies as well. So a lot of focus applications these days, they are about using UAV-aided JRC or for vehicular applications, at least at these higher frequencies. Some of the terms that we'll use later on in some of our examples. So I think Bhavani did mention about multi-user and single-user MIMO, where in MU-MIMO, we are serving different streams, one each for a different user. And in single user, there's just one user and one data stream. Then as far as the simplex, half duplex, full duplex, so here is a diagram which helps in understanding this concept. So in simplex, it's just one-way communications, and there's a single channel. In half duplex, we are sharing a channel, but the communications is both ways. In full duplex, in the standard full duplex, there are two channels and two-way communications. But nowadays, we also talk about in-band full duplex, where there is a single channel, but two-way communication. So there is concern about interference, and in-band full duplex systems, there are a lot of technologies to cancel this self-interference. And we'll see an example later where about in-band full duplex joint radar comms. Which is a generalization of many of these techniques. So here is another way to understand coexistence and co-design. So depending on whether the transmitter or receiver, they are shared between the radar and communications, only one of them could be shared or both of them could be shared. So if it is shared, we call it co-design. And when they are separate completely and they're accessing the spectrum independently with possibly with different waveforms, then that is the coexistence scenario. And in this case, as I mentioned, most of the processing is at the receive end. So in one of the examples that we'll talk about later, we focus on this more general case of co-design, which is this figure D. In this case, the transmitter is shared between radar and communications. It also transmits a common waveform. So this is a vehicular scenario. This is very appropriate for vehicular scenario. It transmits a common waveform which carries communications messages. That waveform is reflected off other cars, which are the targets, and received by this gray car. So now the gray car, which is the common receiver for both radar and communications, admits this reflection from T2. And now the job here is to get information about this blue car, that is its location, Doppler velocity, reflectivity, as well as decode the communications message that was sent by this red car. So this is what we call as bistatic JRC broadcast. Now this could also be in-band full duplex, right? We may not use a common waveform. In this case, we are using a common waveform, but there can be a case where the waveform is also separate, but it is the two receivers, the receiver and the transmitters, they are still common between radar and comms. So this diagram is a very broad generalization of joint radar comms. As I mentioned, we may have a third axis where the waveform is common or not, right, between radar and comms, but then it will be very difficult to represent it on this diagram. So in each category, you can assume whether we are using common waveform or not, and there are then two two types within each of one of these categories. So when we are using joint radar communications, there are certain design considerations. So if I'm using an existing waveform, then I'll just continue with it and I'll focus on just the processing aspect. But if I'm designing a new system, then in that case, I would, for example, if I want to design my own waveform or have my own processing, what is the common metric that I should use to design this common system? And this is a challenge in joint radar communications because in both in communications and radar, the performance benchmarks are very different. In communications, we focus on quality of service, data rates, bit error rate, symbol error rate, these kind of metrics. In radar, because radar performs many different tasks, detection, estimation of target parameters, and if it is a tracking radar, it's also tracking the targets. So we have different other metrics. For detection, we may have probability of detection.
There is a question.
Okay, yeah, let's see. In the chat.
Yes. So the question was, in order to estimate the target parameters in bistatic setup, do you assume the location of transmitter/receiver? No.
Yes. In bistatic case, you have to know the TXRX. And if these platforms are moving, for example, in a vehicular scenario, then this information we can get either through GPS or some kind of, there may be synchronization between the transmitter and receiver. So actually, this is a very valid question because later on when Bhavani explains the bistatic JRC, then you will see we actually utilize this information that is known. But in general, synchronization is very difficult to do in a distributed system. At least at the centimeter wave part of the spectrum, we can employ a GPS, which gives the accurate location information. But as you move toward the higher part of the spectrum, then GPS does not have a millimeter level accuracy. So at millimeter wave or low terahertz, it's difficult to actually synchronize using these kind of devices. And we resort to some specialized communications protocol. For example, IEEE 1588 generic PTP protocol is actually used for synchronization. There are other methods also to synchronize using other protocols. Okay, any other question?
Yeah, no other question.
Yeah, what's the question?
No, sir, you can continue.
Okay, all right. So by the way, how are we doing on time? Because I think it's at 1.5 hours, we are supposed to take a break, right?
Sir, we are going to take a break in 4 minutes, sir, for half an hour.
Okay, so I'll try to complete this part. Oh, it's a half an hour break, you said?
Yes, sir.
Okay, all right. Okay, so I was talking about common design considerations, and usually communications and radar, they have very different considerations because they perform different types of tasks. So in radar, detection, estimation, and tracking are some of the major functionalities. So if detection is of interest, then the metric is probability of detection, which is a monotonic function of signal to noise ratio. If parameter estimation is of concern, then we look at root mean square error of those parameters. And if tracking is a consideration, then we look at the tracking filter error. So it's very difficult to have just one criterion to measure the performance of both systems when you're co-designing them. So this has given rise to what we call as radar-centric ISAC or communication-centric ISAC, meaning when it is radar-centric, then we only optimize the radar performance, and communications is of secondary concern, and then vice versa. However, if we are calling it an integrated sensing and communication systems, it seems very unfair that we focus on just one of those systems. And there may be applications where the performance of both systems is of equal concern. So there is some recent research on using mutual information as a joint as a unified or a common metric. So in communications, obviously, we have this concept of mutual information quite well known. And as you can see, the mutual information that we define here in communication is between this transmit and the receive, given the channel. In radar, Michael Bell, in his work in late 1980s and early 1990s, in his paper on information theory for radar, he proposed mutual information as a metric to gauge the performance of radar. And here the mutual information is between the received signal and the target channel, that is H, given this X, because in radar, the waveform, the transmit waveform is known. The problem with this kind of metric for radar is that although indeed mutual information for radar gives us some assessment of radar's performance, for example, higher the mutual information, in general, higher the probability of detection, but there is no direct connection that is so far known between mutual information for radar and its various metrics. Nevertheless, this common metric has been recently used to design some of the joint radar comm system, and we'll see an example of that in part 2. And then other design considerations that receiver and transmitter, they include a transmitter if we are transmitting a waveform, and if it is if we want to separate the waveform for communications and radar, there are so many degrees of freedom that we could use as far as the coexistence is concerned. For example, different antennas may be employed. Some antenna indices could be used for radar, some for communications. You can separate them in frequency, polarization, transmission slots, and so many other degrees of freedom could be utilized for coexistence. But in co-design, we'll use a common waveform that exploits all the antennas, all the frequencies, and other resources that are available for both comms and radar. And at the receiver, the question is how to actually separate the information from radar and communications. So again, there could be antennas that could be used as degrees of freedom, or in communications, we may use we may estimate the channel states beforehand for communications. In millimeter wave systems, the challenge is that the CSI is changing very dynamically. And in some JRC designs, there is a constant learning that is involved to know the channel state information. So there are a lot of considerations to design these ISAC systems in general. Another concept that we'll very quickly overview is monostatic versus bistatic system. So I think Bhavani did mention about this when we were discussing monostatic radar versus multi-static radar. But here in a joint comms case, especially in a vehicular scenario, so we just looked into the bistatic case. In the monostatic case, a good example will be that you have this vehicle which is transmitting this common waveform. The message goes from this vehicle to other comm receivers, which are on the other cars. And then as far as the targets are concerned, which are, for example, this biker or this pedestrian, the echoes are reflected back to the same transmitter. So there's the monostatic case. One of the advantages of analyzing this scenario from a bistatic perspective is that you may get some kind of a coverage extension in bistatic scenario. In monostatic case, I have the radar has the circular coverage, which is same in all directions. In bistatic case, because we are exploiting the reflection of this target and then the receiver as it is in another location, at least in one direction, I have a longer coverage than the monostatic case. So if I have a way to utilize if I have an algorithm to actually exploit this information, this bistatic processing, then at least in one direction, I will have a longer range. So this is something interesting, and we use it in one of our applications later on. So biostatic is a more general scenario, but then at the same time, it also offers benefits, for example, coverage extension. Recently, there has been a lot of interest in UAV-aided joint radar comms. So although we will not explore this in part 2, and you're welcome to look into our papers on this topic, the difference here is you have all those considerations that I mentioned if you are using radar and communications jointly, but and the channel models may be different in some cases. So there's a lot of work on aerial channel models as well. But there are two important considerations because of this platform. So if the UAV operates in two modes, it may be flying or it may be hovering. And if it is hovering, then there is some perturbation in the platform which you need to take into account while modeling your system. For example, you may want to design more robust beamforming because the platform, there are some vibrations in the platform. And the second consideration is that UAVs, in general, they operate as a swarm, as a group, and they may form either a regular array or maybe an irregular array, and you have to take into account this swarm operation as well while designing drone-borne joint radar communications. Okay, so that ends that segment. Is this a good point to take a break?
Yes, sir. We'll take a break of half an hour.
Okay, all right, thank you.
Thank you, sir. Sir, the part 2 starts at 11:30.
Okay, got it.